So, hello everyone. I'm Shannon. For those of you very new people who might not know me, I think most people do. Pavan has been with me. He was the first graduate student that I had when I joined NCBS along with Shrishti. We were a lab of 3 for a little while, anyways, until we started a lab. And you know, before I came to India in 2014, I was at a Max Planck Institute, and I used to work with engineers. And it was around 2010 that I sat around with these engineers and one night, and we were having some wine together, and we started musing about how great it would be if we could actually follow insects around. And we had this idea, maybe we could, instead of following them around, because that might be really hard, maybe we could somehow make a world for them, a virtual reality. And so this idea has been with me for a long time. And I'm very grateful to NCBS for taking me in and at least saying that this might be an interesting thing to study. But it's very rare in your life that you can say that something that you have dreamed about, that somebody could make your dream come true. And so that's what Pavan has done for me. He has been an incredible student of mine. I really have very few words. I really can say that I do love all of the students and all of the people in my lab. I think everyone has unique gifts, but I can say unequivocally that I will never meet anyone in my life like Pavan. He is very, very unique. He is very special. And it has been a pure joy to work with him. And I have loved doing this work with him. And I have loved building this world that he has built with him. And I think you'll really enjoy his seminar. So I won't take any more time, but to say that no matter what happens, I hope that you go on and to make your dreams come true.
Yeah.
Okay.
Yeah. Hello, I'm Pavan. Nice to meet you now. So the thesis title is Prakruti Maye, using virtual reality to deconstruct insect ecology. So for the unknown, like Prakruti Maye is a Kannada word from Sanskrit roots, which basically means the illusory world containing nature, which is pretty much what we try to reach here, where we can create a virtual reality for insects consisting of naturalistic like stimuli. And that's the word. It's very verbose in English, but I felt this is a bit terse and did the job. So why do we care? The real world is complex. It's filled with cluttered information of trees, landscape, clouds, flowers, grass. And we would call this pretty challenging landscape to navigate. And we have landmarks, horizon, and visual target. But if you see this exact same world under a new light, you'll see a completely different world. And you'll have polarization cues, you'll have magnetic fields, which are huge landmarks of cues which we can't see. We have odor plume, which we barely can smell. We have ultraviolet cues and electric field cues. We have humidity, temperature, and airflow. And they exist, it's just that we don't see them. But most organisms, which are insects, can actually use them and navigate in this real world. And we really can't perturb these things very easily in the field. But if we want to understand these organisms, it's very challenging. And these organisms which I am interested in are insects, flying insects. They do a variety of things in the real world. They suck our blood and give diseases. At the same time, they make our fruits possible, without which it wouldn't exist. They also eat some part of our fruits. And they also disperse and migrate and maraud other crops. So they have huge human consequences, good and bad. And we need to understand, how do these organisms find their objects of interest? It could be a fruit, it could be a human vector, it could be a flower. So what may be. So how do you do that? Traditionally, you go to the field, collect the cues, and manipulate what we can and have some sense. The problem with the field is it's very erratic. The temperature, the pressure, the humidity change a lot. We can't control them. What people do, get into the lab. Problem with the lab, we create an artificial stimuli which is very constrained, very unrelated to reality as what they are used to. And we have some sort of a dichotomy of very little control or a lot of realism with no control. So, and this is a very open problem, and people have been trying to answer this since quite some time, more than when my father was born. Okay, when my father was born. Peter Kunz created this fantastic drum with contrast stripes and let the tiny bee control the world and make it seem like this is as reality. This is long before displays existed as we know it. So this is a phenomenal feat of engineering. And people have come a long way from 1961 to the modern day, where we give variety of interesting stimuli like gratings and bars and spots to understand how they perceive reality. How do they make sense of them? How do they process these cues at the circuit level, and how do they navigate these? So we have learned a lot from them. Yet there's a slight catch. The catch here being biological systems are tuned to ecologically relevant cues. So for one example is this, which these folks can't see, but the image on A, you can see a general scenery of the world. And you scramble that exact image, you just randomize these pixels, and it's this. It's the same number of pixels, same intensity, same distribution, but just scrambled. And what you want to see is you see the reception, like the response of photoreceptors in insects. And what you see is if you look at the black line, it has a particular behavior for these data. And if you have the purple line, it's fully scrambled. And you're like, oh, that's because the distribution of this is not really what we want. If you put a function which fits it, look, we have a function. Now, is naturalistic stimuli just data which you pull from a distribution like that? Not really. So if you look at the information rate which is transferred at these systems, the naturalistic stimuli contains far more information and it's processed by organic biological systems than any model as such. And this is at the photoreceptor level. You can go a bit deeper at the electrophysiological level. And this is a response of hoverflies where you have gratings, which are these black and white stripes. And we vary the contrast. It's very easy. One is black and one is white. You make the black less black, or you make the white less white. You make it closer to grays. And that's how you vary the contrast. And you basically move the world and see how the fly figures out what's the velocity. And what you see is a very interesting thing. You can change the velocity and the respond, or you can also change the contrast. So both contrast and velocity affect the function of these neurons. But you may say, that's very interesting. When in reality, you take that exact same neuron and the exact same model system and give them in the real world. In the real world, the contrast is not fixed. If I ask you what's the contrast of the scene, it's very vague, because will you take just the brightest and the darkest spot? Will you look at my face, which is, it's a spectrum. It's not clear. So the real world is like that. You have the understory, you have the canopy. It's filled with variety of contrasts. It is nothing but these gratings. And in those diverse contrast and dynamic ranges, they behave the same regardless of contrast. So these systems need to be that way, because you want to know what's the velocity at which you're turning. Are you turning 30 degrees per second or 20 degrees per second? And it should not be dependent on whether it was 36 contrast level or 28 contrast level. So it's independent of contrast and it makes sense. And these systems are tuned to that. And therefore, there's value in looking at stimuli which are not just synthetic, which is very controlled engineers, but also what biology reality is. And Ronald Prakruti, like nearly half a century ago, has been doing this in orchards, putting different interesting shaped objects, sizes, colors, smells, and seeing what attracts them most and what is their choice of preference. And these black dots you see on these objects, they are flies which are stuck on it. And they used to manually collect each of them and understand what preferences are. And they did a huge barrage of experiments. This is just one of it. And that's how we know a lot about this particular system. And this is my system too, because we wanted to understand, choose a model system where we know its preferences at the physiological level, at the behavioral level, its consequences at the ecological and evolutionary scales. And very few models exist that way. And one of the models which we chose, which is also solitary, is the apple fly. This is the object of my interest and sitting on its objects of interest. And the apple fly is a fascinating organism with these variety of knowledge which we know well. And we wanted to understand, can we build a VR for them? First step is, does it even fly on a tether? The reason that's important is because we can't track it in the real world. So I put on a tiny rod and saw if it flies. And yay, it flies. It seems like, you're doing a thesis defense, but it's not obvious a priori, because there are so many species out there which have tried, which doesn't fly on a tether. they fly beautifully in reality, but not on a tether, because a tether is an artificial system which is very constrained. Lo and behold, my first ever tether, it flies beautifully, as you can see by the angle of the tether. And yeah, it works. Now, are they really flying, or are they just flying here, flapping their wings, or are they passing their visual input? Are they making sense of it? Are they just panicking? So what we did is we took a tiny toilet paper roll, we put the fly there and moved it around with the contrast paper. And you can see they neatly track, and you can see their tiny feet with this tiny world they're holding moving around, and they actually make sense of reality. This is like the first time, and we're happy. It's sane, it's doing it. We did the same thing on a display, because a paper with a toilet paper is not the same thing as a display, because this reality is a continuous series of not images but reality. But a display, on the other hand, is a series of images over time, 60 frames per second, 100 frames per second. And for us, that's okay, because we are a slow processing system. But insects process really fast, so there's no reason to believe it would work on a display. It worked. They actually made sense of the stripes on the very old ancient monitor, and it made sense. So like, this gave us confidence that we can build a VR and it works for our model system of our concern. So first step is, because we were focused on giving realistic stimuli, we wanted to make sure reality matches virtual. So on the x-axis, you see the angle subtended by a object in VR, and the y-axis is the angle subtended by the object in the real world. If I did my job right, the real world and the virtual should match, and they should be on the 45-degree line. Seems like it is. It is, except at very large angles where you learn in school that small angle approximation is a small angle approximation, so it fails there. But in general, it works. What I show in the VR is what it would have been if it was in the real world. The images match. So that's the visual input, it's calibrated. Now we have to calibrate the motor output. So what do you mean by calibrating the motor output? The fly is stuck to a rod. So I don't know where the fly wants to go. Does it want to turn left? Does it want to turn right? Because it's stuck. To address that, Peter Kunz again, long ago, they made this elaborate ingenious system called the compensator, which in Deutsch is Das Doppelspulen. Hopefully I get it right this time. And it is an interesting system to figure out how much the fly wants to turn in these micronewtons, very small amount of forces, to see whether it's turning. This is very interesting, but very hard to do. Modern day folks, what we do is we measure something called the wing beat amplitude difference. Basically, you see this is the fly beating its wings happily, but we want to know what the fly is doing. So we measure the blur of the wing. So what do I mean by blur of the wing? So if the fly wants to fly straight, it would beat its arms or wings equally hard. But if it wants to turn right, turn left, it would beat its right arm harder than the left. Does that make sense? Because you're pushing more on the right, so you end up turning left, you generate a torque, and you do that. It's like riding a cycle or swimming, for example. Same thing when you're turning right, you push more on the left hand side. So this is what flies do. So we measure these angles, and in real time, so if the fly says it's 30 degrees, so many degrees left, I say, okay, you want to turn left, let me move the world right, which is what happens when you're in a train or VR, any game, for example. You press the left arrow key, the images in the monitor turn right. So this is updated 187 times a second, and therefore the fly is essentially using its wings as a joystick and controlling the world. So the fly is playing the video game, thinking the display or the stimuli it's getting on the monitor as a reality, and moving on. Oh, by the way, if you have any questions, feel free to interrupt me. I forgot to say that. So, are there any questions? I shall wait for 15 seconds. I assume none, and I'm going forward. So this is basically the fly doing this. Now, there's a slight catch, because I said if the fly says it's 10 degrees on its wing, it doesn't mean it wants to turn 10 degrees in reality. So this is where it's confusing, right? Because if I take 3 steps forward, I took 3 steps forward. And if I knew my height and my gender and my race, I can tell you this is the distance I have traveled. But for flies or anything which is in a fluid, it's not so straightforward. So many wing strokes. If I take 3 wing strokes forward, it doesn't mean I moved so many centimeters forward. I would have moved 1 centimeter forward. Sometimes I would have moved 10 centimeters back. It's completely dependent on the environment too. It's very non-trivial. So therefore, there's no obvious way to say that, okay, if there's 10 degrees separation in the left and the wing beat, make the world move so much. It's not obvious. There is no right answer. So we had to figure out this gain. So that's why we're going to do a driving test for flying insects. So here you can see a truck driver in the city in Kolkata, and obviously moving the steering wheel in crazy ways, but the vehicle is barely moving. And then you have Formula One, Hamilton turning a little bit and going crazy. So, and it's important, it is the way it is. If Hamilton was here, if Hamilton's turning system was here, the entire people would have been wrecked and casualties. If Hamilton had this wheel, he would have never been able to make that turn. So it's important to have the right gain in the right context, but it's not obvious what this number is. So we can't ask the fly, so we do a driving test. And what do I mean by driving test? So I basically move the world clockwise and counterclockwise in various terms. So on the x-axis is time. On the y-axis is the velocity at which I'm turning the world. I'm turning the world clockwise and counterclockwise at various speeds. As the y-axis goes high, you're turning so much clockwise or counterclockwise. And I see how the fly responds, the response, which is like using its wings. And I see that for small speeds, it works well. Beyond a point, boss, I can't do this, I give up. And it does it. So, and this is what it does generally. Now, if I reduce the gain, it gives up much earlier. If I increase the gain, it gives up much later because it's much more range to do it. So if I give a low gain controller, obviously a sharp turn, the vehicle can't do it. But if I give a high gain controller, you can even do a sharp turn. There's a catch. The catch here being, I take a high gain controller, even the slightest tremor of a hand will be amplified. So, and that's where we come to something called maneuverability and stability. It's a term where in terms of closed loop, we measure how well the animal can turn to these various turning stimuli and how stable it is. And we see that as you can increase the gain, the stability falls. As you increase the gain, how well it can turn works. At very low gains, as expected, it's super stable. At zero gain, it's the most stable. It doesn't turn. It's super stable, but it can't turn at all. So it's zero maneuverability. On the other hand, you have very high gains. It has very low stability. It's jittery as hell, but it's super maneuverable. So now what is the right range? So we vaguely define this fuzzy region where they're comparable as a stable region. It's not a number. The number is not special. It's the region that matters. And for our flies and most of the flies we tested, it's roughly in that region. However, much of VR research which has happened in the field has constrained itself to lower gains due to technological constraints primarily, and we are stuck somewhere there. So it's slightly away from the optimal regions, and therefore we implore the researchers to actually use the gain which is appropriate for their model system so that they can actually do things. Because if you don't, you basically take a Hamilton and put them in the truck and hope they do magical things. And more often than not, they can't. And that's where much of the research is. So once we are calibrated, we wanted to see if multimodal VR is feasible. It is. We actually could give systems and they could make sense of this in this jaggy landscape. So like this gave us incentives. So like, let's build it right. So this is how we were doing initially for parameters. A lot of numbers, obviously very hard. We made a slightly less clunkier version so that I could see the trajectories, what they're doing in live and adjust them. So now we build this. Finally, this is how our VR is. After a lot of iterations, we have a very high refresh rate display with giving and airflow and odor. So that's a monitor which the fly is seeing as reality. The fly is in the center of these capillaries. The capillaries are giving it airflow and odor. The camera is watching what it's doing, and that's the lights, which most people ask. So this is a fly. See, you have all of it: airflow, odor, vision. Now let's see what we can do with this finally. So how do flies navigate to targets in complex worlds? It's not obvious. We have landscape, we have background, and you have to figure out what the foreground is. It's not trivial what is the tree. Modern networks still struggle to do this. And organisms somehow seemingly make it easy. So this is how the VR is. This is what I am seeing as a first person view. That's the fly in real time coming from the camera there. That's the trajectory. And I'm monitoring what the fly is seeing there in this corner and its turns. And I'll now go inside the arena. That's a triangular arena where I get 360-degree visual airflow odor input. I open it up for you. In the center, you can see the fly. The fly is over here. And this is the first person view of the fly, kind of. And you can see it beating its wings, looking at a bunch of pixels, perceiving it as reality, ducking and weaving through the leaves, looking for where the hell the tree is in this url. It's not there. In the next one, it comes. And duck and weave and try to go towards the apple, throw out its legs and try to land. And it'll keep doing this again and again and again, when in reality, there is no tree. And so now we do this enough times, now we have data. So the red dot is where it began. That's my fly. And the gray lines are the paths the fly has taken. It has gone all over the place. The circle you see is what we call a polar plot. And what you see is the length of the line tells how straight it went. If it's straight, it'll be very large. If it is curly and going in circles, it's small. And the direction is in which direction it went. As you can see, it did not go in any particular direction or with any particular determination. On the other hand, you give the same fly a tree, you can see it goes straight towards the tree, consistently, steadily, with a large low standard deviation. So it goes straight to that, circular variance. We did the same thing with mosquitoes, male mosquitoes to trees, and they also happily do it. We also did with hoverflies and to flowers, and they also do it. So we did with multiple species, and they all convincingly go to their objects of interest, figure out which is the background and foreground without hassles. Yet modern marvels struggle in more often than not.
Pavan,
Yes.
how do you figure out what the landscape would be like in the non-tree landscape? And
Oh yeah, so we know about. Oh, you mean the non-tree as in the
the landscape.
oh, hold on. You mean this part?
Is it important? How do you figure out?
Oh, it is very important. Great question. Basically, if you don't do it right, they'll actually go to clouds and stars. If you don't set the background right, you will assume they go to particular patches of the sun and everything else. They think it's a bright dot. So, which is why if you see in this 360-degree view, there's no sun. The sun is eclipsed here deliberately by Photoshop because they go to the bright spot. So it's important what the landscape is with no clear bright spots.
How do you figure out like the green part?
Oh, it's a tiled but non-repeating. How do you say? It doesn't look tiny at the angle of the fly. That's the prime, and it's grass textures, and the texture is scaled to the size of the fly. In the sense that if the fly is 1 meter away, the grass should look like what the grass would look if it was 1 meter high in the ground. So it is mapped to that. So if I take you to 1 meter height ground, how the grass would look, it would look the same. So, but it is important because we have to make sure the clouds and skies were right, because if you had just one light, because as a photographer you generally try to get the golden hour and put at evening 5 o'clock sun, and they basically had a side bias. If you give 2 trees, they used to go to one tree more often than other, and that's when I realized that you need to have 2 suns so that the shadows match up and it's right. So these subtle differences between shadow because of sun is at an angle matter, so we have to put 2 trees. So all of those tiny things matter, not shown here for brevity.
You have to figure it out.
Yes. It's not obvious. No, this was the one that works. Many things failed.
Even this is ecologically relevant in terms of.
It's from the landscape which they are. Also, this is the same grasses which grow in the region where they are found in North America. So I asked my friend to take a 360-degree view over there, pulled it out, and made it from it.
Yeah, that's what I mean.
Yes. Yes. Yes, sir.
So my Dickinson used to give the fly a choice between bush and Clinton.
I hear you.
Consistently, the fly would go to Clinton.
Yeah.
And that happened because Clinton occupied.
Absolutely.
So if you were to give a choice between a tree and a pole,
Yeah.
or something that's obviously not a tree,
Yeah.
what
I did. So now it depends on the contrast of the pole. If the pole is pitch black against a pitch white background, they go to that.
Yeah, so then,
But if it is not, if it's contrast match, they go to the tree. Now, as a scientist, would you choose the contrast match one, or would you choose the black one?
well, as a fly, I'm thinking.
But you are the scientist giving the input.
So, how important is it for the tree to look like a tree? Is my question.
Pretty. So we'll get to that. So I put the tree upside down, they go to the right side of the tree. And I put a billboard tree, they go to the rear 3D tree. So there are a lot of other breakdown things which we do. But yes, the tree has to look pretty much reasonably like a tree. Now, if the leaf was instead of here was there, or the fruit was here or there, does not matter. It's not so strict. It's about the structure which is there. It's not necessarily this particular tree.
But if the tree was in the pole or something like that.
It matters. So if the pole was pitch black and it's pitch white, they'll go to the pole. But as a scientist, you shouldn't do that. You should choose the contrast match. Then they go to the tree. Now you'll say, okay, now let's make it matching the shape of it because it's just a vertical. Ultimately, you end up making a tree. So that's the bottom up, this is the top down. Both of them are right. Yes. Go ahead. Sorry. Go ahead.
So if you are testing different insects in your machine, how long does it take you to adjust for the different forces the insects produce?
The very first time or after it's optimized?
How to optimize?
A minute or two. It's important because with bees it was tricky because they just don't like to fly a lot. So by the time I optimize their gain corrections and make sure they're centered over there, they generally stop flying. Or I'm bad at tethering bees. Both of them are equally explainable. But with other insects, a minute or two is more than enough, max, and they're ready and they'll fly non-stop. Huh?
Because kind of like I once wanted to collaborate with a Rhagoletis guy, and that in these older versions. Then he said, okay, if I put in a B, it just destroys my apparatus because the force it is producing is way more than that of the
Great question. Ours does not measure force that way. We measure camera, so it does not matter. It's a rigid tether. Put whatever. In the same arena, we put a Drosophila, we put a huge Daphnis moth, works beautifully fine. No issues. So a moth.
matter with the machine. I mean, with the kind of
You just use a different kind of needle. So basically, I use syringe needles. So I use a different gauge. I use a lower gauge, but it's still the same push fit connector, so it works. I can put a moth and the camera works, and I put a Drosophila, it works. No change in the system. The capillaries have to change. But yeah. Can you speak up a bit?
Do you always do your experiments at the same time of day?
I mostly do in the daytime before 6 because diurnal cycles. For moths, I did in the night, and mosquitoes, I did in the evening. They asked me what time they do the experiments. So they do that, and I do that with different species. Is that clear? No. Oh, yeah. Go ahead.
You said you put 2 suns in the arena. Why didn't get that? Because even in real world, there's one sun, so one tree will be getting more sunlight.
Yes, you make sense. But now that's why field research is hard, because in field research, the sun keeps changing, and if you want to do any real experiments, you have to keep track of it. You can't kill the sun, hold on there for a moment, let me finish the experiment. It's hard. Whereas here, I can, and therefore don't let that affect my things. I'm not trying to see the effect of 2 suns on insect behavior. I'm trying to see the effect of the trees on the behavior. I don't want the sun to affect. And the way to do that is either put sun in the middle position, which is tricky and looks ugly. So I put two suns so that it's nice lighting. As a photographer, you'll see 2 lighting and bouncing off nice. So I don't want to see the effect of 2 suns. I want to make sure they do it right and consistently right.
So you end up with the 2 trees will look similar.
Identical, pixel to pixel identical. It's not same or similar. So now we want to see how they do for different targets and distant targets, because beyond a point you can't see it. We put trees at different distances, and what we saw is this is a heat map. So the amount of green indicates how often they stayed in that region as a fly, many flies together. And as we go further, the probability of they reaching the tree reduces, and beyond a point, it's practically 0. And I can tell you, for a 3-meter tree, beyond 24 meters, my fly, Rhagoletis pomonella, will not reach the tree. And you may ask, what is the meaning of this number? Why does it matter? Why measuring these numbers matter? So if any of our research matters in the real world in the sense of agriculture in some sense, you need to know what is the acuity or the limits of your model organism as a pest modeler or as a dispersion modeler, or if you're modeling pollinators, you'll know what is the distance each individual agent can do, and you need to know these numbers. It's pretty challenging to measure them in the real world. With here, it's pretty easy of how easily can you reach your object of interest. And you may ask, well, I can measure it easily. I can just give a grating, make the grating fine, and you can tell what this. Some people will tell this is the limit. People with specs is somewhere here. Zoom call will be even higher because the compression will ruin it. Now, is that really the limit of your perception? Not really. Reactive distance in some sense is what is the smallest font size you can reach. And again, that's different too. But that's an object of salience, and that's different from the smallest pixel or the intermaterial angle you can measure. And that's what people care, because your object is not always one intermaterial object size away. And that's what I wanted to make, that with reactive distance, you can measure these numbers in the lab and actually help ecological researchers in some sense, in one aspect. So now the next part is how do they estimate depth in flight? And you can see these two trees look identical at the start, but as you go closer, one of them is bigger. It took away my thunder, but yeah, it'll loop back and you will see that the closer tree, both of them are expanding, but the left tree is expanding faster than the right tree, which is expanding. So it's not trivial to estimate that if you're trying to write a vision algorithm, because first you have to figure out what are the objects in the field, distinguish that from the foreground from the background, and then measure what is the object size, measure that in the next frame and see which object is which, then measure the object size, then measure how fast it expanded, whether it expanded, then measure in the next frame and measure how fast the expansion happened. So you're basically measuring the second derivative of object size and then keeping track of that same object and saying, okay, this is the closer one, and go. So essentially flies estimate depth by using regionalized motion parallax cues and make decisions. And it's very challenging if I had to ask you to write an algorithm for that. It's tough, you can do it, but yeah, so this is the two trees and they go to both equally well. But if I give one tree, which is twice as big, but twice as far at the starting location, meaning which is the red dot, they look identical. Yet they go to the closer tree more often than not. And that's how we know we do it. So motion parallax again is a weight term. I'll get to that in a moment, but yeah, so we can show that they do this, which is very hard to do in the real world. Now, moving objects are distracting. So we want to do for airflow. And the way we did airflow is we gave a pipe and we sucked the air around it with a vacuum pump and made it feel like air coming from different directions. But they generally go crazy because the pipe is moving and they react to the visual object of motion. So moving objects are distracting. It was a lot of fun handling them. And this is how it is. Obviously, it's distracting. So instead of going to the object of interest, they just keep going behind the object. It's just a large object. So what we did is we put a veil like a burqa and tried to prevent them from seeing the object, but they can feel the airflow relatively and hoped it would work. And we covered it in the blackest of black velvet you can get. And can you see the pipes? Most of you can't. Sadly, if you're a fly, you can pick up these tiny specks. So this is called Fresnel reflection, where even the smallest things at curves can see. You can see my nose have a shine with oil and sweat. And every object has that. Even the blackest of black granites will shine at oblique angles. And here you go, when you go through a curve, you go through all possible angles. And there'll be a bright spot and you keep following that bright spot. So basically, you can't make things invisible. So I basically built 101 ways to not build a wind delivery system because it all failed. So finally, the only way to make things invisible is hide it behind a wall. And that's how we finally reached this design, where I give airflow from the bottom. It splits into 16 parts and comes out of 16 capillaries in the top, except there's a catch, that there's a middle pepper shaker, which is a revolver, and it's a tiny hole. Wherever it's aligned, air exits. Wherever it's misaligned, it exits out, not to the fly, but to the dump. And by adjusting this in real time, I can control where the airflow is coming from. And I can make air in any direction without them getting distracted. So this is how the capillary is, and the fly is in the center of this capillary, of these capillaries. But they can't see the moving part because it's behind the black object. So this is how we calibrate visually. We also with an anemometer, obviously, but you can see the airflow basically turning the jet around and moving the air around. That's how I know that all capillaries are working without blocking, basically making sure it works. So this is how the airflow works, the logic is. So you saw the capillaries. So depending on where the fly is, in the middle one, for example, the middle fly, the airflow for the fly is coming from its slight right. So therefore you see that the capillaries on the slight right is pumping out air. On the other hand, on the top fly, it's going upwind, so it's getting from the front. On the other hand, in the bottom fly, it's coming downwind, so it gets from its butt. But I do this in real time. I have an arbitrary windscape setup. And based on where the fly is in the virtual world, based on its angle and on the windscape angle, I set up the motor. And this is in real time. I have a closed loop airflow input and create any arbitrary windscape you want for the fly. And that's why it's called Rasen Shuriken. For people who know it, they know it. For people who don't, they don't. Now let's see what we can make sense of it. So huge biomasses move all along by migration and dispersion. So this is Amur falcons in the millions in Nagaland, which migrate, and they are migrating, trying to catch dragonflies, which are migrating all along the Indian subcontinent. And they are migrating because they are catching tiny insects, which are migrating all along. And these things are flying on the winds of what we call monsoon. And basically, you have a huge biomass and a huge web of life following up and down. And all of it comes back to how tiny insects disperse and move with the wind, because they're not flying, but they're getting carried by the wind, but they're controlling how they carry, or that's what we think. So to understand that, it's very hard to manipulate monsoon. So what we do is we kind of have a rudimentary version of it. We create a featureless environment because they are mostly migrating in the night at height. So there's very little optic flow, and we give it airflow. So this is how the airflow logic is. And we see we give the wind towards the left and they happily go downwind. We give the wind to the down, they make a U-turn and they go downwind. I give to the right, they make a right turn and go downwind. So they happily can perceive wind direction without any visual cues, because there's a concern that they could be doing using slip. Yes, this is a tethered system. So some artifacts exist which don't exist in the real world, but as it is, they can make sense of directional airflow cues without vision. So I also did at different velocities. The first one is I don't give it any airflow, so they go all over the place, which is what the violin plot at the bottom says. The y-axis is angle 0 to 360 degrees, and it's basically a histogram. So if it's very bulgy there, that means it's tighter than that, and it's more of the data is dispersed in that. So it's uniformly distributed, so it's all over the place. As you increase the wind flow, it gets tighter and tighter. And at 3 meters per second, it's mostly going downwind, 180 degrees angle with respect to wind. Yet, at that exact same velocity, if you put a tree upwind, they choose to go upwind. So they're not getting dragged down by the wind like, okay, go down and just get along. They are choosing to go downwind unless they have something to go against for some object of interest or something else. So that's what we show. And we did this in the lab in a couple of months in VR. So this was in the Death Valley in California, United States. And they released hundreds of thousands of Drosophila and tracked it overnight of where it is many kilometers away, 15 kilometers away in a night, and saw its dispersal abilities. This was done in 1980s and recreated again last year. And this was our data which you saw. They mostly go downwind, and as the wind speed increases, they get more directional. And this is pretty much what they saw. As the wind speed increases, they get more directional, and the x-axis is wind speed, y-axis is directionality, which of the two. And this was, which came out a year later. And this was a 6 years of phenomenal hard work and field research waiting. Okay, today is 2 meters per second wind speed. Let's see what happens. Okay, well, let's hope the wind goes down and do it. So it's very hard research, very deterministic, very hardworking people did this. So you can kind of recreate that in field too, in VR too, which helps us have more manipulative powers and do interesting things, which is tricky with the field, as you can imagine. So that was wind. Now with odor. So odor moves in very complicated, interesting, pretty ways and painful ways. And it's not obvious what is the direction or the source of odor. Any questions till now? No. Go ahead. Yeah, it makes sense if you think about it. 3 meters per second is very high airflow velocity. They would not go upwind unless they have a reason to go to upwind. And they can control whether they want to go downwind, crosswind, or upwind. And they fully do that. Insects go downwind most of the time unless they have a reason to, when they, for example, on reception of odor, for example. And they go crosswind so that they can sample much more. So their behaviors are very distinct and depends on the organism, but they go downwind all the time.
So if you present an odor in the downwind phase, it changes it.
Yes, even vision, for example, changes it more than odor. Odor is slightly more trickier, but even vision, as you can see, could change it and make them go upwind at the 3 meters per second, not the lower.
The idea being that you're just wasting energy going upwind.
Yeah.
If
Unless you encounter.
yeah, unless you encounter something
Totally.
that give you energy.
That is my hunch. But if I say that, then you'll shoot me down. If you say that, it's okay. No, I fully agree with you. I really think that's what's happening. But I have no way to show that the energetics dynamics. I have no evidence to say that. It's my hunch. It's a very good hunch, I think. But yes. Huh? Yes. No, I agree. No, but I agree. That's one explanation. I fully makes sense. This odor is very interesting, and the odor, as most of us have been taught in school more often than not, doesn't go by diffusion as primarily. Diffusion is a very small aspect of it. It mostly goes by advection. The airflow odor goes based on how the air goes, and air goes based on complex fluid dynamics and how the boundary conditions are. So this is how interesting it looks. That means you can get source level odor concentration far away, and the likelihood of you getting odor packets, as we call these punctate tiny pulses, is reduced at farther away, but when you're close, you get at higher frequencies. So that's what we do. We couple it with wind, and when you're far away from the odor source, you get very low frequencies of odor. When you're higher, you get more beep, 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 higher odor. So it's something like a metal detector and goes beep, 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 beep when you're close. And we create this thing, and when you're outside odor, you get nothing. So we create this again in odor. I have a capillary which gives odor too. So I have 360-degree odor and airflow in closed loop. We calibrate it with a PID. PID is a machine which detects how much odor, volatile compounds are there, and we basically see the different pulse durations. We see how it responds and figure out the sweet spot of our system. We calibrated and we chose numbers which work with our range. So now the video which you can see in a moment. So you will see the trajectory of the fly, and you'll also see what the fly is seeing, and you'll also see the fly itself, and you'll also see one tiny green bar which goes beep beep when you receive an odor, when the fly receives an odor. As it goes closer to the odor source, it gets more beep beep beep. And it's, I think, doing some tortuous, high tortuous turns at the high BP regions. And then beyond a point, it exits the plume. So it's now slightly changed its way it's moving. It's slightly moving in interesting ways with larger step size before it makes the next turn. And it will also reacquire a plume in a bit. If you give it time, it will do interesting things. So
There's a little delay.
yeah, there's also yeah, it's now on the plume. So this is what we did. We did this many times, and when there is no airflow and no odor, it doesn't go to the odor source. When you give it just odor, it doesn't go to the odor source. If you give it just airflow, it doesn't do it. But if you give odor and airflow simultaneously, closed loop airflow and odor, airflow is always there. Only then they actually can follow plumes. If the wind is stuck in a particular place, it doesn't do it. In summary, what I've told you is
So the video that you showed, there was no visual reference.
so yeah, that particular video doesn't, but we give a tree far away, which at the starting location you can't reach. And you know where I got that number from the long ago slide, that they can't reach that no matter what. And so that's just a landmark. When they come close enough, they will see.
But if there was a visual reference,
Yeah,
would it still do this thing?
great question. I don't think so. It doesn't. So yeah.
How often do you see that it localized to the
Yeah.
odor source and then it is just, searching?
Yeah.
So is that representative of most of the data?
So they get tortuous as the odor concentration, as the number of packets they receive. Like if I plot the tortuosity as a function of how many packets they receive in the last recent past, it's a function of that. As not linear, but as you pump in more odor, they get more turning. So insects navigate to multiple species navigate to virtual objects in complex environments. We can measure critical ecological parameters in virtual reality. Flies can compute localized motion parallax cues on flight for decision making, which is different from when they're sitting, because many mantises and many other insects peer and provide perceived depth by moving and giving extra IPD is what we call interpupil distance. But they can't do that on flight. It's very tricky. So they use this. Flies use airflow cues to navigate without vision. And finally, flies need both airflow and odor for plume following. So now we'll ask, what's the point of this slide in the grander scheme of things? So this is a beautiful image of how mosquito repellents and other repellents have helped humanity reduce malaria. Maybe, but if you go to the darker side, quite literally, is how this is done. So you have mostly young African males and 20 to 25 sitting in malaria prone regions and sitting with feet exposed with a tiny suction pipe and measuring how many mosquitoes bit them all night. And these are wild mosquitoes, and some of them have gotten a controlled treatment of a repellent, and some of them have got something like an odomos. And that's how we see the efficacy of it. And that's how we get all our odomos and everything. So we are running on their blood. So quite literally. But our hope is by using VR, we can put mosquitoes in VR, which we have, and give them relevant targets and put relevant repellent compounds and see which of them do the task and screen them. And out of 100 compounds, I can tell a few of them which will do a better job and then do that in the real world. So it's a screening thing. VR is not a replacement for reality, but it's an aid for doing reality-like experiments easier and faster, cheaper, a more ethical way, and see it. So this is a tiny Aedes aegypti male going to a tree happily. And we did that with other species too. You can see it. So you can see it bobbing and weaving and going towards the tree, and that's the trajectory. We did that with a crane fly, which is one of the local species here. It's a beautiful fly, and even they do that in a moment. Just watch it. So that's a fly looking at a bunch of pixels and perceiving it as reality. Now this is a crane fly, and even they do that. So many insects do that. And they're also controlling it. As you can see, it's on a slightly lower gain, because these insects like lower gain. They're very slow, dandly-like flying things which don't move really agile ways. So even they do that. They don't really go to apple trees in reality, but I had an apple tree with me, so I put it. This is a hoverfly, and they go to flowers. So let me pause for a moment. And you see there's a slight difference here. You have trajectory, field of view, and the insect. You also have something called flight speed, which is the speed at which the fly is flying, and that's controlled by its wing beat amplitude sum, how vigorously it beats its wings. And you can see how the flight speed gets affected. And the fly is flying fine with some speed, and as it approaches closer to the flower, you can see a stark decline in its translational velocity. You see a slow gradual decline and it going to close, and it's basically doing a hovering action, and it's also called a hoverfly. So we can sort of recreate even hovering action in the fly. You can see it's closer to the blue line, which is 0 velocity, so it's just hovering and chilling there. So this is what we can do in VR, and we can also do other things in terms of pure science, not just translational research. That is, we can do wonky things like this, which seems wonky, which is the fly. This is the top view for you to make sense, and that is reality. And you can see the students. The tree has some issues in life. It's going around and moving, and that's deliberate. It is moving in a particular way, which is not obvious unless you go through it. So it's like a rainbow right now. So, and it's doing different things. They have very small aspects of how they behave altered. So motion parallax is not one thing. It's a fuzzball of things. So imagine you are going on a train. Before we go on a train, imagine you're running forward. Objects closer to you expand faster and become bigger, and that's why they're closer to you. The further ones expand slow. That's looming part of it. But if you're in a train, you're looking sideways, perpendicular to your direction of motion. Nothing is getting big. Really, nothing is getting big. What's happening is the closer things move much faster, but the further things move much slower. That's called scroll, which is what happens in Mario, for example. That's how you get a sense of depth. And at an angle, you have all of these components. So what we did essentially is individually disable just scrolling or looming by basic. So if I give you an example of, if I have to say, make the object stay that size, but not become big, that's how this interesting things happen. So this is reality. So when you get close, so you can see that's a twice as big tree, which is twice as far, but that scrolls much more than this. And that's because how geometry works. But if I screw it up and artificially turn off or turn on scrolling, and you can see the dynamics are different. You have to observe very carefully. It's extremely confusing. That's why it's virtual surreality. It's not obvious. And we want to see like whether they're using a looming part of the spectrum or the scrolling part, because the algorithms to compute these features, if you're writing an algorithm in computer vision, it's very different. And we want to see how are they teasing apart these things, and we want to do other things. And finally, This is a Drosophila, and we have done phenomenal things with its research using interesting stimuli. But if you do give it a chance, it can also do interesting things by giving them trees. So we implore that we can also learn biology from other ways besides being an engineer. Says the engineer. This wouldn't have been possible with many people, starting with Shannon's. Hold on. Any questions?
I had a question.
Yes.
One of the previous slides, like from the beginning. Don't go. Not it. So how do you quantify maneuverability and stability? And I was thinking like if I have really high head, but still there will be high maneuverability, but if I can break myself very quickly, or like I have a lot of inertia, then I could have good stability.
Yeah. So mosquitoes, for example, have a gain somewhere on the other end, 96. Like,
So that was for apple fly.
yeah, no, that was for apple fly, but I have for other species, and mosquitoes are on the other end with 96, whereas crane flies are on the lower end. So different species have different things, and that depends on their life history and their wing beat frequency and all of those things.
And how do you quantify those stability and
Mean and standard deviation of the difference between the impulse and the response.
do they get used to a game if they are typically not used?
Certainly, you can even give negative and they handle it fine. People have done that for the past 3 decades. They will learn, but now that's where the catch is. Insects, flying insects generally do something called a saccade, which is like a very rapid, brief turn, which is almost ballistic. And that's generally in the order of 100 milliseconds. But more often than not, people have seen saccades in VR and tethered systems lasting for many seconds long. Strictly speaking, that's not a saccade, but I see saccades lasting for 100 milliseconds if you give them the gain of that high. So if I go back here, so if you see this, do you see these tiny excursions at high velocities of turn? You'll see these tiny spike-like things, like almost like action potentials. Those are these brief saccades which are like 100 to 200 milliseconds long. But at very low gains, I don't see that. They can't even. There's no output. They try to do a saccade, but nothing changes. There's such a low gain.
So the presence of those things tells you that they're in the right. You're in the right range.
At you only see that at high gains, as in gains in the gain of this at these regions. At these 6 gains, you don't even see the saccade. Nothing happens, so they just don't. You only see those gains. You don't see those brief saccades over there because they have to turn so many degrees, but they have not turned at gain 6. Gain 6, typically the field is in 2, 3 in that, and that's at 36. So that's a factor of 10 or 15. So that's how it's 10 to 15x longer. That's my hunch.
How it was visual cues and how it was stability. But if you try doing both these trees, does it give more importance to only one of them?
Those were the next questions we plan to answer, and those are great questions. Yes, we do not know the answers yet, and this is a great tool to do that.
So I'm wondering whether short distance or long distance gives different importance to different kinds of trees.
Yes.
Or if you continue to what is happening.
Long distances, likely they're going to use odor. That's what we know from field research long before, with very interesting experiments by putting bubbles in the world. But yes.
So actually, I wanted to ask a question exactly about this, which we have this slide. So this is a key result, and in many ways it throws the light back on many old papers. You explained one of the results that is problematic, which is the saccade. But there must be many others that are also problematic. Can you tell us about a few?
So saccade is one, and the second is how people look at when they see it's very smooth and stable, but their vision is jittery. And much of the reason is also because when you're doing calcium imaging and other things, if the stimuli changes too fast.
That's recently. I mean, they've been doing this for a while.
Also, they have done gain research before earlier too, 60 years ago, long before, and they chose high gains. Somewhere along the way, the gain, and they chose the right gain by measuring torque, like the literal gain. This is mine is cartoon gain because it's with image based. So that's the literal gain, and they use those high gains. But later on, the field stopped using those high gain values, both in torque based or in BW difference. I don't. So that happened after the masked image, the GOATS 1983 ones, where they put the photosynthesis mask. The display challenges, because you can't update it fast enough and other issues. That's when it stopped going to those segments.
So will be analyzer, but will be analyzer is clearly rapid.
That's fast. The display part. It was on a drum, no longer on a drum, and then later on you also have limits on the drum to how quickly you can move the drum. You had mechanical constraints. Then you had LEDs are also slow. They can't turn as fast, so they can't update as much as quickly independently. So, for example, Andrew Strauss' work, they artificially clip the max update rate. Though the gain is high, it's like you imagine a gain, but you put a clipping function. Basically, you can't cross this line. Even the line here to other people, like line of like 50 or something, even though you're sampling at those ranges. So you're clipping it artificially. So it's artificially clipped all along in the field due to multiple technological constraints, which kind of eased up with us. Any other, there's questions on the cloud?
Online questions, please.
Yes. Go ahead, Mukund.
Okay, thanks. I think Upi also had, but I'll go ahead. So Pavan, based on the last few things you said about scroll versus looming,
yeah,
I mean, those would be sort of heuristics for computing distance. Whereas, what one should be doing is something like maximum likelihood with a few parameters, 2 components of velocity and assumed object size or something like that, right?
Yeah. So go ahead.
Is there any basis to think that the organism is using a heuristic because it makes some errors in a systematic way?
Oh, it certainly makes errors. And I have seen when I've played these, like when I've made the insects do it, that they use both the components. And my hunch is like when you are, they do these curvy business. So if they are not getting head on like looming cues, for some reason, they kind of go at an angle. So they sort of get the scroll cues. So they are not stuck to a particular algorithm or strategy. They can make use of these things in interesting ways. Now, I don't know if I answered your question. Do you have any other, if you can articulate more precisely, I can, or differently, I can give
Yeah, I mean, so you were saying if you were to write an algorithm, it would be complicated. But I thought the algorithm would be just simple. It would just be maximum likelihood. But to express that algorithm in terms of scroll and looming might look a little messy. That's what I'm trying to get at.
Yeah, so I'm not trying to express it as scroll looming. Scroll looming is the way I can decouple, because the only player is theta, like cos theta. So if it is perpendicular to the direction of motion, you get zero loom, you only get scroll. If you're head on, you get
Did you take it out from your from your stuff which you brought?
I think
Okay, sorry. If you are fully head down, you get complete loom and zero scroll. At an angle, you get this. So I imagine when they're probably parsing this based on the angle of the object with respect to the central vision field, and having a transform based on the theta is the way I was imagining. Because these cues are continuum. It's not like loom and scroll are independent. It's the 0 and 90 are the extremes, but it's a fuzz area where you have both all the time. So I think they're using something on those lines. It's a hunch.
Hi, Pavan, can I go?
Yes, go ahead.
So, Pavan, thanks for a great talk. And I have to say, this is the very first thesis seminar at which I ended up with a video game headache from motion sickness. But that aside, it's great fun to see this all packaged so nicely, and so many nice open ends to follow. I had a couple of questions on those lines. Did you do a psychometric curve to assess the relative strength of different stimuli in the animal's decision making?
So I did not do. I initially started off the psychometric approach of having different grating contrast and different thickness, and that did not take me much places. And I'm like, let go of this. Let's start from the top down, and let's start with the tree and break it down. That's where I went. So I abandoned the psychometric approach of calibrating with different optic flow velocities and see how they decide, because decision was kind of like this binary and you needed object. So that's why I abandoned the psychometric approach. You started with psychometric.
You could do psychometric with trees too. You don't have to stick to gratings.
That's Aditi. So Aditi, for example, is doing that. So, and that's
okay.
A step where you can do in VR2. In VR2, you can break it down. That's like you can just turn off the branches. We made it upside down. We make it flat. So we basically don't get 3D depth, like local motion parallax. You make it upside
But so Pavan, sorry to short circuit it, but I was actually thinking of facing off different modalities.
That's a detail. Come back in a few months.
Okay.
I know, because Aditi does that with messing with vision and olfaction much more.
Oh, fantastic.
Exactly decision-making behavior in pure behavior. Not
Okay, and so a related question, which maybe Aditi will answer for us, is whether the summation of the cues of multiple modalities is linear, non-linear, priority-wise. How is it done?
It's non-linear, which you can see in the last one, because you give it just vision or no vision or odor, wind, it doesn't work. You have to give it all the three together. It's non-linear there, but very few systems in biology are linear. So it's non-linear, which is a free answer which I can give you, but I also have data to show it's non-linear.
Right, but what kind of anyway, yeah, what kind of non-linearity?
It has to be synergistic in the sense it has to be together. They can parse them independently, but they only work really well in tandem.
Okay, okay, that's great. Thank you, Pavan.
Any other? Yeah, go ahead.
Hi. So I have a couple of questions, both are relating to kind of how naturalistic visual stimuli are. So how does how does the total amount of light compare to like sunlight?
Great question.
I'll
finish that.
Second one is about polarized light. Many insects with polarized light, to navigate this one. So,
Great question. Both of them not even close or close, depending on how you see it. So this is around 1,000 to 2,000 lux, which is not really a lot, objectively speaking, when compared to sunlight. It's not, but it's reasonably bright. It's not too dim. It's the brightest amount money can buy. So it's the brightest hue. It's fully maxed out in contrast and brightness. So in terms of polarized, the cues are polarized, but not in the way reality is. The displays are polarized always for free, but I can't manipulate the polarization. Like not with this setup. So it's uncontrolled. Again, next color. It's RGB. RGB is tuned to human RGB, long, medium, and short. It's not the same for insects. So in all these cases, it's a flawed system, but it still helps us understand many things. It's not a replacement for reality, but you can still do many things. Any other questions? I don't see hand. Oh yeah, go ahead.
So this is in context to your core experiment.
Yes.
And I'm assuming here you took the sum of the
yes. Yes.
Does it happen in all experiments or is it a special?
Hoverflies do that very good job. Others really struggle. Now, is that a fascinating thing about hoverflies, or is that because I don't have enough N? I don't know. But generally, when I try to give closed loop for other flies, they just went wonky. Now, is that because I don't know how they fly in the real world? I don't have a reference. But hoverflies, I know what they do, at least one part from their name itself. They generally hover on target. Is that the reason? Because most real insects don't hover. So I do not know if it's due to reality or because of that. But hoverflies did the great job, others did not.
So to follow up on this, so in the hovering, it's not necessarily based on your wing amplitude, right? Because other aspects of wing also changes. So you cannot measure, just so essentially you gave the fly different kind of control and yet it's doing what it's supposed to.
Which is really not surprising considering how amazingly smart and cute these things are, that they can make sense of anything you can give them. It's just that hoverflies are really good at making sense of things stop in reality, which others are not. It's probably their vision system being able to do that more than their motor systems. And that's probably why. But yes, the angle of attack, none of that is in control. There's a very cartoon thing, but they made sense. It's like we doing video games. It's not reality, but I use it. I'm good at video games. I use in that.
It also means that you can ask questions regarding the interpretation. It has nothing to do with flight as long as you give the input as you become.
That's my hunch. That's my hunch. As long as you give reasonably relevant things. If you're trying to assess hovering in, say, Drosophila, I don't think or other insects, it's probably not worthwhile. With hoverflies, there's a chance, despite being flawed. Any questions on the cloud?
I have lots of questions, but I'll ask you later.
Sure.
Okay, all right. So thank you, everyone. I hope you will come back around 7 o'clock wearing pajamas for Paula. Okay, I'm already expected to tell me whether he actually passed it or not. But right now, we will have a little private chat with him for a little while. So please come back and enjoy the rest of the defense. Okay? It's not actually.
Many years ago, one a PhD student was defending, walked out very stressed out that she'd forgotten her acknowledgements.
Oh shit! Thanks a lot. I should have
It's
finished.
our fault we asked you all this question.
Yeah, so a lot of people was needed to cross this bridge, and it wouldn't be impossible. Shannon, Sanjay, and Upi being on my thesis and my advisor, like wouldn't have been possible. Marianne was the a student from Germany who helped me make the 3D trees look real. He did a great job of it, as you can see. Dora Babu, Hinal, and Shayan, without which I couldn't have done anything with my experiments. They got me the flies and helped me take care of it a lot. Dorababu, Srinam, Shubha Umesh, they helped me all along building the VR all along the way, Abhin, Vaibhav. Madhusudan sir, who without which I wouldn't have even decided to do research, along with the planetarium. Professor Chandru, Ganesha, and Umashankar, the Trinity, which without them I would have even chosen biology because biology was boring collection of facts. Anna, Amma, Valli for being there all along, my family and friends for making it happen, our funding agencies, my lab, the institutes, Microsoft Research, and Stack Overflow for making it happen. And last but not the least, them for standing in line, waiting in patience for their turn and doing it. And people will ask me, or if you're uncomfortable, the white ball is the thermocol ball, which is like their pacifier, like that's where it's filled with sugar water. So they just sit like their world and they don't fly until I take it off and it's like ready to fly.